Hey, good morning, everyone. So my name is Nigel. I'll be presenting about this paper. So this is going off what Dr. Snabel actually presented this morning. So I'm actually a graduate student with Dr. Bhaskar, who actually, as Dr. Snabel also said, is the one who has the longest last name in the ISU directory. So a little bit of introduction. So we'll be focusing on the tassel of a plant, which is the male component part of a corn plant, which is also responsible for the producing of the pollen to sort of for the reproduction of like the growth of corn. So the idea what we're trying to do is that we're trying to answer the question, how is tassel development and morphology is affected by the genotype and the environment that it's growing in. So not only do we want to see like the genotype or environment individually, we want to see the combination of both, how it's going to affect the development and the morphology of the tassel over time. So a little bit of motivation. I'm sure most of you know the current methods are most of the time very labor intensive, tedious, and also very cost intensive. And also measurements, taken by hand is very subjective between people. So what we're trying to do is we're trying to create an automated phenotyping method that does that automatically. And currently, most of it is either done in small scale or in a greenhouse. So this is the setup that Dr. Snabel said as well. We have about 5,000 NAM genotypes, and then we have 486 20 megapixel cameras. And these cameras will take picture over a period of 2 weeks, and from like 8 a.m. to 5 p.m. every 10 minutes. So you can imagine how much data this is going to generate. Although if you take one camera, 8 a.m. to 5 p.m., that's 9 hours, and you take every 10 minutes, that's going to be 6 image an hour, and then you multiply that, and then you get 54 image a camera. But then now multiplied by 486, this blows up. Technically, with each it being 20 megapixel camera, even when it's compressed because it's a lower consumer level camera, you're still getting a 9 megabytes per image. So if you again multiply it up, you get over 3.5 terabytes or even more at the end of the day. So that's an example image of like the image that the camera captures. So now the analysis challenge, like I said, it's going to be a large data set. Logistics, analyzing is still going to take a very long time. And also, we'll be having a lot of problems in terms of like if you stand out in the field for a period of 2 weeks, you're going to be experiencing different kind of weather. You're going to experience cloudy, you're going to experience wind, rain, thunderstorm, hopefully not tornadoes. Because we are looking at 5,000 genotypes, we have a lot of different tassel morphologies. They will grow up, they're going to look different, they're going to be shaped different. But these are things that we are trying to look at. But then movement of tassels, in the span of 2 weeks, some tassels will grow and some will go out of the camera and stuff like that, as well as sometimes leaves come in the way. These are two problems that we actually cannot solve at the moment. We cannot reconstruct missing images as of yet. So as you can see, we have different light and shadow at different time of day. So going off, the first problem once we obtain the picture or image from the camera is to identify the tassels. We have to figure out where the tassels is to analyze them. So we are using surf detectors to find out where are the point of interest in an image, and then we figure out if it's a tassel or not. And that's where bag of features come into play. The reason why we use bag of features is because the training time is fast, and because we have such a large data set, you want the training time to be less and the analysis time to be shorter. So bag of features actually converts those features into a set of numbers, and then a set of numbers is what a computer does best. It's able to analyze really quickly. So you can see that it's converting, and because surf detectors actually, we use them is because they are scale invariant, they are rotational invariant, they are translational invariant. So if a tassel changes its direction, angle, we still can capture it. So going off that, this is how a bag of features looks like. So we have two sets of data set. We have to prepare it like we have a positive set and then we have a negative set. So in the positive set, it's all tassels. And in the negative set, we have everything else. We have leaves, we have sky, we have clouds. So we can tell the program, hey, if you take a look at this, this is a tassel and this is not. So from here, once we train those features and construct those histograms from the previous slides, and then here is an example image that is captured by the camera, we extract those tiny portions of the image using the surf detectors, and then we compare those images with the one that we train, and then we can classify whether this particular image is a tassel or not. And then from there, we can construct these tiny images back into a tassel. And then once we identified where the tassel is, the next step is analyzing them. So we use basic, So we use basic like graph-based algorithms. So this is where it actually comes into play even in our day-to-day life. We see graph-based algorithms in Google Maps. You choose point A to point B, but then you get like 3 different routes, and then it tells you one is slower, one is faster. That is maybe 10 minutes slower depending on how it works. So that's what graph-based algorithms do, because you'll be able to see like this route is longer or shorter, or depending on traffic too. And also we'll be using basic morphological operations to obtain the basic traits of the plant. As you can see here, this is also we use the algorithm shortest path, but then we use the longest path to extract how long a tassel is, for example. And then once we obtain the tassel images, we have to figure out which is the foreground and which is the background. And then because of the previous challenge that I mentioned, that there's going to be various weather that we'll be experiencing over the span of 2 weeks. There's going to be clouds, dark, light, bright sunshine and everything. So as you can see, this is a picture of a cloudy day. So you can see most people usually use odd-source thresholding to figure out to separate the foreground and the background, and this is what happened. So because we have so many combinations of weather possibilities, we have to use a consensus-based thresholding or a voting system and say that, okay, so these 4 images look alike, so we'll figure this works, this thresholding methods work. If it doesn't, it flag the image, and then someone can go in and manually do it. So if we have a large data set, no one is going to be able to look through every single image to figure out threshold value for it. So these are a couple basic traits we're able to extract right now easily. So we can have like the pixel count, convex area, and everything like that. So moving on, now that we're able to extract it, we can move on to the analysis part a little bit, which is right here. This is a very nice plot. So basically, like right now, that most people are categorizing open or closed morphologies with 2-number system, which is 0 or 1. 0 for closed, 1 for open, for example. But then now, because we're able to analyze it on a very large scale, we're able to say, put a number and say like maybe 1.2 times 10 to the power 5 pixels in terms of convex area. We can say that this tassel is an open morphology versus a closed morphology for anything below it. So from now on, instead of a 0 to 1 system, we have a greater variability towards our classification. Also, this is a distribution over diversity, so it's basically saying over a number of populations that we have looking at. So you can see that in tassel wave, we have an idea how a tassel looks like, if it's low or high, or for example, if the perimeter of a tassel is low or high. So also for distribution over time, you can see how a tassel grows, if it's from small to large in terms of perimeter or convex area. So these are important in terms of like if maybe a breeder in the future, he takes a look at this and he's going to have intuition on how to how a certain type of genotype will grow over a period of time. Also, I developed a really nice GUI to visualize the data and say, because now we have a lot of data, we're not going to be able to look at all the numbers, but then we can plot it out and we can see. So we can say, we can plot pixel count, we can plot convex area versus tassel width or tassel length, and then you can see, if you select a point, you can see this is the tassel image, how it looks when it's thresholded and how it looks when it's analyzed, as well as the temperature, humidity, wind speed data at that point that you selected. So there's a couple of stuff that we've done. So going off, because this is a large data set, we actually had to deploy it on a supercomputer. So what we actually use is MATLAB. So because most people have it and it's easily accessible. So we parallelize this thing over 15 nodes, and each node have about 16 processors. So we have about 300 over processors, or basically computers, if you think about it. It takes about 5 minutes to analyze a camera image, and if you analyze it on a CPU at home, it's going to take 3 to 4 years. But then if you parallelize it over 300 computers, it actually took me about 4 to 5 days. So if I add in anything else, it's again going to take me 4 to 5 days versus 3 to 4 years. So my conclusion for this is that I'm sure everyone understands that right now computers change the landscape of everything, and now that we are using computers in phenotyping of plants, I believe there's a very big potential in improving a lot of stuff. Also, this concept can be easily expanded for other plant science problems. It doesn't have to be limited to corn, but it is right now. But we can expand it to soybeans and everything. And that's all I have. Thank you.
Questions?
Just wanted to ask whether you tried GPU computing to increase performance.
We have not, but
Okay.
we will be
It
thinking
will be
about that in the
interesting
future.
to see
Yeah.
whether you can get improvement.
Yep.
Okay.
Thank you for that suggestion.
You mentioned you could apply this to other than corn.
Yes.
Can you comment on how easy would that adaptation be? I mean, what would be the challenges, differences?
Well, the basic thing that we just need to change is the positive and negative data set. We just have to say, instead of a tassel as the positive data set, we just have to figure out what we want to analyze it. And then we can say whatever we don't want is in a negative data set. And then we can extract whatever the object of interest, and then change a little bit of the morphological operations in terms of what we want. Because once we convert it to graph, we can get anything.
Got it. Very good. Any other questions? Yes.
So, relative to identifying the tassels, so if you have a plant that's an individual plant, or there's some reasonable separability between the plants, then you can identify the tassel quickly and then get at the issue of actually extracting the specific features. What kind of limitations did you find relative to, say, high density plants in the field, occlusions? Did you have, because many times you'll be in the field and you'll have, tassels will be waving around, and unless you have some really strong positioning information to separate this tassel from the one that's behind it, then there's some difficulty. So what limitations did you find?
Well, we do find one thing, that most tassels sometimes do look alike, but in a camera image of 6 tassels, usually we are able to correlate pretty well. We can get previous information and then compare it to, because it's every 10 minutes, we can compare it with the next 10 minutes and say, okay, it's right there. So we're actually using location and image correlation base and say, this looks alike and it's close by. But then, there is still sometimes that we do have errors and inaccurate predictions, but most of the time, location and correlation does the job.
I think we'll keep it quick because we need to move.
Did you have to block everything by height? Because otherwise you'd be looking up at the tassel, and if there was a taller thing behind it, it would get in the way. So did you have to plant all your plants according to height?
I don't think we do that, but we actually point the camera at an angle that faces up. So we don't see anything behind that tassel. So we'll be using the background as the sky instead of using a wall, so that we can do this in a large scale. Right. Thank you, guys.
All right, very good. I think we should thank the speaker.